All right, let's dive in. Today, we're setting off on a quest to understand the invisible force that powers pretty much everything in our modern world, electricity. We're going to learn the secret language engineers use to control it, starting with our biggest challenge. This. Yeah, take a look at that. At first glance, it looks like a chaotic mess of lines and symbols, doesn't it? Well, this is an electrical circuit diagram, and you can think of it as a map of invisible forces and flows. Our mission is to figure out how to read this map and predict exactly what the electricity is going to do. So that's the real question, isn't it? How do we take something we can't even see, something that moves at almost the speed of light, and turn all that chaos into order? How do we build our phones, our computers, our entire digital age out of it? Well, it all starts by laying down some ground rules.
To even begin to make sense of this, we first need a way to visualize what's going on. And the best tool for that is a really simple but powerful analogy.
I want you to imagine that this whole complicated circuit is just a bustling city. The wires, those are the roads. The current, that's the flow of electricity. That's just the traffic, the cars moving through the streets. And the voltage? Think of that as the traffic pressure, maybe the steepness of the hills pushing all those cars along. This one idea is the key to unlocking everything else. Now, any city that works well needs traffic laws, right? Otherwise, it's total chaos. Well, to tame electricity, the first pioneers had to discover its fundamental laws. These are the absolute basics, the toolkit every single electrical engineer has to master.
And first up is the big one, Ohm's law.
It is so elegantly simple.
It just says that the voltage, our traffic pressure, is equal to the current, which is our traffic flow, multiplied by the resistance. And what's resistance? It's basically just a narrow, bumpy road that slows traffic down. This little equation, V equals I times R, is the absolute bedrock of all circuit analysis.
Next up, we have Kirchhoff's two laws, which, when you think about it, are really just common sense for our city traffic analogy. The current law says that the number of cars going into an intersection has to equal the number of cars leaving it. Simple, right? Cars can't just vanish into thin air. And the voltage law says that if you take a round trip through the city, you always end up back at the same elevation you started from. There's no net change in that pressure. These rules are what prevent total gridlock. Okay, so with these basic laws, we can figure out simple circuits. But what happens when that city becomes a sprawling metropolis with millions and millions of roads? Well, the basic rules become impossibly tedious to use. Engineers needed shortcuts, and they needed them badly. And that's really the heart of the problem. Trying to use only Ohm's and Kirchhoff's laws on a modern microchip would be completely insane. It'd be like trying to find a route across the entire country by calculating every single possible turn you could make. You'd be lost in a web of equations forever. This problem of overwhelming complexity is what drove the search for more powerful tools. And this leads us to one of the most brilliant shortcuts ever invented, Thevenin's theorem. Now, what it claims is pretty astonishing. It says you can take any part of a complex circuit, I don't care how complicated it is, and you can replace it with just one voltage source and one resistor. It's like having a GPS that just ignores all the city streets and gives you a single direct path to your destination. It's a game changer.
And this just shows you the power of that idea perfectly. You start with something that looks like that nightmare diagram from the beginning. You apply the theorem and boom, it collapses into this beautifully simple equivalent circuit. And the amazing part is, the behavior is identical. It's like an act of mathematical magic, and it's what makes designing modern electronics even possible.
Okay, so now we have tools for steady, one-way traffic. We call that direct current, or DC. But the electricity that comes out of the walls in our homes isn't like that at all. It's alternating current, or AC, which is constantly reversing direction. And this presented a whole new level of challenge. You see, the problem is that AC current and voltage aren't steady. They move in sine waves. They're constantly wiggling up and down. So the simple math we used for DC just completely breaks down. A new, much more sophisticated language was needed to describe this constant state of flux. And the solution was absolutely brilliant. It's called a phasor. The best way to think of it is like a stop-motion photo of a spinning wheel. That spinning wheel represents the oscillating sine wave. A phasor is a vector, an arrow, that freezes that wheel in time, capturing both its length, which is the wave's amplitude, and its angle, which tells you its position in the cycle or its phase. Suddenly, messy wave problems turn into simple geometry. And with this new language of phasors, we needed a new concept to go with it, impedance, which we represent with the letter Z. You can think of it as the big brother of resistance. While resistance is just a simple roadblock, impedance is a much more complex opposition to AC flow. It takes into account how components like capacitors and inductors react differently depending on the frequency of the AC wave.
And this slide just sums it all up perfectly. In the nice, steady DC world, we talk about voltage, current, and resistance. In the wild, wavy AC world, we upgrade our language. We now talk about phasor voltage, phasor current, and impedance. With this, we're finally equipped to analyze pretty much any circuit you can throw at us. So why does all this math and all these strange new words matter? Well, because these abstract tools are the actual blueprints for the real, tangible technologies that define our everyday lives. Let's connect these equations to the electronics we all use.
Using phasors and impedance, engineers can design the filters inside your speakers that know how to separate those deep bass notes from the high, sharp treble. They can design the massive power grids that have to stay perfectly synchronized across thousands of miles. They can even design the tuners in your car radio that lets you lock onto a specific station.
Let's just stick with that radio tuner for a second. It works on a really cool principle called resonance. At one very specific frequency, and only one, the opposition from the inductor and the capacitor in the circuit perfectly cancel each other out. The circuit's impedance suddenly drops, and it allows just that one radio station's signal to rush through loud and clear while all the others get blocked. It is a beautiful, practical application of AC theory.
But these laws and these theorems, they didn't just appear out of thin air. They were discovered on this long quest by generations of brilliant, dedicated, and sometimes pretty eccentric human beings. So let's meet some of the minds who actually drew these maps for us.
So, on the left here, we have Arthur Kennelly, who helped develop the very concept of impedance that we were just talking about. And on the right, that's Pierre-Simon Laplace, the Newton of France. His powerful mathematics gave us the tools to analyze how circuits change and react over time.
And I love this quote from Laplace because even he stood on the shoulders of giants, telling everyone to go read the work of the great mathematician Leonhard Euler. That's how science works. It's this great chain of discovery. Laplace's own incredible contribution, the Laplace transform, is a powerful tool that can turn the really complex calculus of circuits into simple, manageable algebra.
And that legacy just keeps going. You've got Oliver Heaviside, a reclusive genius who did foundational work pretty much by himself from his attic. You've got Charles Steinmetz, who standardized the use of the phasors we needed to understand AC. And of course, there's Nikola Tesla, the visionary who championed the very AC power system that has become the lifeblood of our entire planet.
Ultimately, this whole quest, from Ohm's law all the way to phasors, has really been about one thing: carefully observing the physical world and then creating a language to describe it. And that leads to the final and most thrilling question: what else is out there, operating by rules we haven't even begun to decipher yet? What invisible forces are just waiting for us to finally discover their language?